Okay, so I'm Adam, creator of DeepLearning4j, as Alexi has kind of already said. First of all, I'd like to screwing with me, man. Hey, come on. All right. So one thing I'd like to announce is I'm writing the O'Reilly book on deep learning, Deep Learning: A Practitioner's Approach, with my co-author Josh Patterson. He co-presented with me at Hadoop Summit last year. Speaking of which, we're also going to be we're actually going to try to present deep learning on Spark this year. So we did Yarn, we prototyped it, got some good stuff going, and now we're going to be doing deep learning on Spark. So what I'm going to present to you here today is mainly going to be focused on the architecture. So getting you familiar with neural nets, because okay, actually let's stop there. How many of you guys actually know about neural nets? Like, okay. How many of you guys have actually coded with them and actually used them in production? Woo, all right, more than I thought. Okay, so how many of those were just backpropagation, or did you actually use deep learning? Okay, yeah, backpropagation. Welcome to the 80s, guys. All right, what I'm here today, I'm here to catch you up to 2015. So I'm going to cover today, one, the core architectures that involve different kinds of deep learning nets, and then I'm actually going to kind of bring it back down to the code. So you're going to see visuals paired with code. So the idea here today is to get a practical understanding of neural nets, how I apply them, and what, in my opinion, is actually a modern machine learning architecture that allows you to plug and play with different kinds of knobs, and everything's configurable. So the problem with current machine learning libraries, this could be Weka, this could be MLlib, yep, I'm trash talking. Things are brittle, things are pre-configured, and in general, things don't tend to be, you can't do anything. Like, you have to submit a pull request to Spark whenever you want to update it. This is as a Spark 1.2. If there's any MLlib guys in the audience, bring it. Let's, inform me, teach me something. Because what I did was I went straight to building on top of Spark. Obviously, I'm an implementer of a deep learning framework, and I specialize in neural nets. I've done machine learning for a number of years. I've used the algorithms, but there's been distributed machine learning algorithms around for a long time. Spark is just faster, which, obviously, it's the de facto platform today for any sort of MapReduce paradigm computing. So that being said, it's worth building on top of. But I have my own opinion about what an architecture looks like, and that's what I'm going to present to you here today. So to start, I love the JVM. I've been doing it for a number of years. Distributed computing and where the data lives, that's all on the JVM. There's basically, if you think about the Hadoop ecosystem, Spark, it's basically a fork of Google's ecosystem in open source with something that you use on a day-to-day basis. Hadoop is now over 10 years old. Spark has been around for quite a few years now as well. It's now a top-level project in the Apache Foundation. So things are great for the JVM. The JVM is still the future. So what I'd like to do is kind of bridge the gaps between scientific computing and research with GPUs, like what a lot of these guys emphasize, and native computing, which you actually have in your data center, all brought back down to your Spark or Hadoop clusters. So to start, so what is deep learning? Why should you care about this? What's going on here? Most of you guys are doing machine learning. You guys are probably specialists in some domain where you know every single little piece of your data. You understand what the features are. You understand what things do. But at the end of the day, if you're trying to do text, if you're trying to do unstructured data, there's nothing to make sense of that. If I'm an NLP practitioner, which that was primarily what I did before doing deep learning, you gotta think about, well, if there's a suffix here, it begins with a capital letter, or maybe if you're doing images, there's all sorts of crazy transforms you have to do. You have to build edge detectors, you have to apply filters, and it gets brittle. So ImageNet, for example, before deep learning came along with convolutional neural networks by LeCun's group and everybody else at Google and everybody else, you basically had a series of hacks. So you had you had all these different auto feature engineering libraries. You see OpenCV. OpenCV is just an abstraction for a lot of different kinds of feature engineering. Deep learning actually gives you an elegant solution to feature engineering with unstructured data all in one algorithm. So the problem with neural nets, though, is they're slow. They're really slow. They're impractical for day-to-day use. So what I'm here to do today is to place an emphasis on distributed computing and actually make it so that you can iterate on models and use it in your day-to-day. Because the problem with neural nets is that they also require a special pipeline. So while MLlib is amazing, it's fast, real time, there's streaming, there's all sorts of algorithms, neural nets require a special kind of pipeline. The features of neural nets are typically output from other neural nets. So I'll actually demonstrate that here today and kind of give you an overview of why you should care, how you should think about neural nets, and then applying that back to distributed deep learning. So now that we've kind of seen deep learning, so let's talk about this feature engineering thing. So why is it hard? So humans perceive cats. Humans perceive, but computers only see numbers. You see pixels, 0 to 255. What do you do with that? You apply edge detectors, you smooth out the image, you get rid of noise. Think of it very similar to Photoshop. What I'm here to do is actually show you that deep learning basically has a built-in Photoshop system that actually knows what filters to apply and when. So the core idea with deep learning is unstructured data and automatic feature engineering. So what's it good for? Basically, any machine learning application focused on unstructured data. While deep learning is great for other algorithms, or other kinds of problems, it won the Netflix prize. It was part of the Netflix prize with recommenders. It's broken records in image and speech analysis. Both of the systems that are in speech recognition, in face detection, all records broken by deep learning, all with automatic feature engineering. So think of it as basically a subset of machine learning that gives you automatic feature engineering over unstructured data. So what can deep learning do that other applications can't? How about image caption generation? This used the output of a convolutional neural network trained on images, neural word embeddings from Word2Vec. I'm giving you a bunch of terms to Google search. I'll be more than glad to answer questions later. And what's called a recurrent neural network, or a long short-term memory neural network. So a convolutional neural network was trained on photos. A neural word embedding was trained on a corpus. And then you have a recurrent neural network that learns to actually generate the captions. So I'm going to go into what each of those neural networks are. This was actually a fresh result just from last November. And several actual companies have actually been able to produce results with this. So if you want to automatically describe images, if you want to augment search, you use neural networks as features. So how does deep learning actually work? So deep learning focuses on this automatic representation learning. You start with raw data. So focusing on vision, because that's the canonical use case, we have pixels. We have cat pictures, like I mentioned earlier. And I want to train it to think about cats. So we'll start by first building an edge detector. So you have one neural network that allows you to kind of detect edges. It kind of figures out just direct patterns. Then you have the next layer that actually learns, well, oh, there's these edges actually form parts of a face or parts of an animal. Then you finally have the final layer, which actually figures out what a full cat looks like. And it's basically what you do with deep learning is you have 3 or more layers. That's the deep part of it. You initialize it on the raw data with one neural net. You take the output of one, pass it to another. It learns the next set of representations, and so on. And then all you do is you tag logistic regression on the end of it, and you have a classifier. The key here is that these neural nets all do a form of feature engineering. The automatic feature engineering works with unstructured data, learns the patterns, and gives you a good representation that you can then use for cutting-edge classification. So just to give you an example, so this is actually from DeepLearning4j. So this was run on the labeled faces in the wild data set. The neural network was a restrictive Boltzmann machine, and it actually outputted actual faces. These are actual neurons. The weight renders you see are actual neurons. It actually learns to reconstruct the data. So in general, this is done with standard convex optimization techniques, gradient descent, LBFGS, conjugate gradient, anything that basically minimizes an error with respect to a loss function. A neural network itself is a universal approximator that can learn any function. In this case, it also does a nonlinear transform on the data to give itself a representation that it can then use for feature engineering. So now what I'm going to do today is I'm actually going to open up the box on neural nets. In some frameworks, you do val type is equal to a new deep learning. What does that even mean? What I'm actually here to show you today is what the different neural network architectures are, how they work, and I'm here to open up the black box so that you can actually understand what kinds of neural nets are there, how to think about deep learning, and how to actually build your own applications in a practical context. Part of the problem with deep learning today is that most of the frameworks are either requiring you to derive your own equations, or sometimes you have an automatic derivation engine, if you're looking at Theano, or you can't scale it out, so you can't work it on a distributed system. So what I'm here today is actually kind of show you how to bridge all these gaps and actually give you something comprehensive that's practical and actually realistic for deep learning applications. So the first is the canonical feed-forward neural network. A feed-forward neural network has an input layer, a hidden layer, which is the nonlinear transform. Think of that like the sigmoid function or any of these other kinds of algorithms, and the output layer. It's a series of logistic regressions that basically output yes or no. That was the first representation that thought of the brain where the neurons fire. But you can in general think of neural networks as a 2D logistic regression. You can actually use that analogy to learn most about neural networks. So what I'm here, so we've seen this. There's feed forward and back propagation. So that's the standard way. That's the only neural network most people see. So one thing I'd like to tell you about is that there's actually a feed forward architecture you can use for automatic representation learning. So for those of you who are familiar with standard backpropagation neural networks, you have an input on each neuron. You have an input, you have a connection weight, and you have a bias. What this actually gets, so what happens if you add another bias though? So that's called an autoencoder. There's two biases, one on the visible that's attached to the input that knows about the original data, and the output. The output is what you'd think of with the normal bias on a backpropagation neural network. What it does is it minimizes the difference, in this case, for those of you who want to Google search something, KL divergence, or the reconstruction cross entropy of the original data and the output. So those faces that you saw were actually the connection weights turning on and activating on faces. So I had a visible bias that was attached to the original image, and I had the output, and it minimized the difference between the input and the output, which gave you those reconstructions. For vision specifically, that's actually a debugging tool. For neural networks, you don't actually debug them just by changing a number, running an F1 score. Debug them visually. So the problem with working on a cluster is it's not exactly obvious how you troubleshoot something, especially with something as visual as neural networks, where there's all sorts of knobs that you have to worry about. You want to debug them visually. DeepLearning4j's architecture actually allows you to prototype the algorithm in local, just like you would in Python, and then scale it out in a cluster without rewriting one line of code. So debug visually and locally, work with vectorization in either Spark or in DeepLearning4j, and then scale it out in a cluster. So another kind, recurrent neural networks. So just like I mentioned earlier, so recurrent neural networks are for time series. So they're for learning. They learn sequences. So that image caption generation you were seeing was actually a neural network that pretends to be a hidden Markov model. So it actually learns a sequence. So what it does is I feed it features in, and it learns how to predict future values. This has been done with all sorts of algorithms, like time series, text, anything where there's a sequence of something. You can actually use, so for those of you who know machine learning, it's a generative model. So again, it also learns features. So the next one is a convolutional neural network. A convolutional neural network is the best thing for vision. It's also broken records in sentiment analysis, as well as recently by Jan LeCun, word embeddings. So you can actually train a neural net to recognize individual characters and build a better language model. So a convolutional neural network, the basic idea is it breaks a space up into parts called a feature map. And what it does is it almost like uses like a little eye, and then it trains each part of the eye to identify different parts of an image or different parts of a problem. So those feature maps that you're seeing then get aggregated or pooled. And then what you get is basically an aggregation of all the different parts of a problem into one space. Not only do you get reduced space, reduced memory, but you also get a generalized representation that's position invariant. The other one, this is a little academic for some people. Another one is called a recursive neural network. A recursive neural network is basically mainly for text. It can also be used to break apart a problem for vision. The idea is that you have a tree, you have a binary tree specifically, and you basically take two parts, the children, you combine them, you compute a score, take the next one, so another child, and you take the output, the aggregation of the two, combine them, and then you go up the tree. And then what you get is a representation that gives you something that learns sequences or individual contexts. So this is called this uses something called backpropagation through structure. So other than that, let me show you one more visualization of scene parsing, and then let's get into some code. So one of the things I wanted to do here today was kind of get you familiar with just the different kinds of neural network architectures in DeepLearning4j. I've implemented all of these architectures. All of these are the core representations that you think of as a layer. So that's what I'm going to kind of show you next is some actual code now. So this is breaking apart a scene just like what we represented before. So from here, what I'm going to do is I'm actually going to show like different parts of the code now. Let's see. So the first thing to think about is that everything is a layer. So when you're thinking about these different kinds of neural networks and you want to mix and match them to do different things, everything's a layer. So these layers then basically have all this idea of mini batch training. So you'll see like activations, inputs, outputs. It's just like what you see with any neural network. So any recursive neural network or any of these other kinds of neural nets will actually just be this representation. So you combine, what you typically do with deep learning is you combine them together into a multi-layer network that you then use to run your classification or do your generation or what have you. So think of everything, just implement this interface if you want to create your own layer. So if you want to create your own neural network, it's actually a plugin. That's it. So basically, it's a general purpose architecture for neural networks. So the idea here is that rather than treating them as a black box, learn them, combine them, and use them. Learn about some of these new applications, because the key here is that neural networks are used in combination with one another to produce a lot of these results, the cutting edge results you're seeing today. So let me see. So the other thing, OK, so the other thing then is this idea of a multi-layer network. So the multi-layer network is how you combine layers. So you combine layers by taking the output of one and putting it into another. So this is how you build convolutional neural networks. This is how you take the output of like a recursive net and pipe that into the another neural network, and then you have some form of final output layer. You then use that in combination with other neural nets to, I don't know, you can do classification with it, you can generate image descriptions, doesn't matter. Key thing here, this is actually how you aggregate other neural networks. So basically the idea is this is basically a support class for you to implement your own neural networks. You have a general purpose architecture that you configure in core, and then you scale out with Spark. So before I get into any other code, are there any intermittent questions or anything in particular people want to see? Yes, no? Okay, one pass.
So it's hard to read.
So, okay. Yeah, say something, please.
It's pretty tough. Can you give it a white background? That's a little easier.
Yeah, I didn't expect that. Hold on. Let me see. Actually, you know what? Let's go to GitHub.
That's easier.
All right. So it's open source, people. Just remember that. So in core, okay. Better? Okay. All right. Good now? Okay. So here's the thing. A multi-layer neural network is literally a series of layers. The way I designed it, every neural network is a plugin. That's what I was talking about. You take the output of one and put it into another. Did you guys want me to show layers again, or did you guys get the general idea? I mean, basically, think back to the visualizations. Every one of those is a layer that you then use for the multi-layer neural network. Okay, so let me go ahead and actually go back. Okay, I can see that. 1 second. All right. So okay, multi-layer configuration. All right. Okay, so like I mentioned earlier, the other thing is this idea. Everything's configurable. So so basically, what you do is you actually create a multi-layer configuration. This configuration is what basically it allows you to instantiate a neural network. You then basically, how it works with Spark is you basically take this configuration, you use the autocomplete in the IDE. So remember, Scala and Java are statically typed languages. Use the tools presented to you. Use the tools that you're given. Allow the IDE to actually help you actually discover what the parameters are and what the knobs are. And allow yourself to ask questions. So the multi-layer configuration is basically built in the IDE, serialized to JSON, and given to Spark. So basically, in core, you prototype everything locally. You run the visualization pipelines that I was showing earlier. In this case, working with the renders if you're doing vision. Or if you're working with text, I actually have something called T-stochastic neighbor embedding built into the framework that actually allows you to group and visualize words. So one of the cruxes of deep learning with text and why a lot of people haven't done it is because they don't actually understand how to use neural word embeddings. I'm not going to go into that rabbit hole right now, but I'll say this. You basically use, you debug neural networks visually. Images and text are by far the major ones. But another thing you can actually do with neural networks is you can also debug them with histograms. So one of the tricks in neural networks is you want to actually monitor how fast they're training, how fast they're learning. If they learn too fast with too few iterations, they're going to overfit, and you don't have an accurate classifier. So do everything visually, prototype it locally. The histogramming support I have right now is currently, I don't like this, but MapReduce. So we're actually using that to actually render a lot of the visualization tools. If any of you guys have any JVM-based visualizations or web-based, I would love to hear from you. So in general, prototype locally, scale out with Spark. So what I want to do real quick is just basically show some example usage now. So I'll just pull this down here. Oops. Let's see. So what does this actually look like then? Let's see. So actually, I have. All right. All right. So what I'll do is let me show this actually related to Spark now. That's what you came here for, right? All right. So what I actually have a sample. I actually already have a sample application on Spark that gives you kind of an idea of what to do. So let's just kind of go through this now. So can you guys see it? Good. So in Spark, you set up your configuration. So in this case, I set a few different options in here. I'm just using args4j to parse the results. And basically, all I'm doing is I'm setting up a configuration. So like I mentioned earlier, you use the IDE's autocomplete to basically give you kind of like a discovery mechanism for figuring out what options are present. How do I configure a neural network? So neural networks, one thing to note here is that all of them have this idea of hyperparameters. Neural networks have over 60 hyperparameters, and you have to understand how each one works and how they interact with each other. There's a variety of there's an infinite number of configurations that you can do. So one of the things I want to mention here is that you'll notice how I have this idea of a layer factory. So a layer factory, just it sounds Java. I come from that world. You're more than welcome to give me a pull request for something Scala-based. But basically, you have a layer factory that knows how to create a layer. So that layer is basically how you create a series of stacked neural nets that learn features. So remember, deep learning is hierarchical. You take the output of one, it learns the raw inputs. Take the output of the first one, pipe that into the next one, et cetera. And then you build your classifier. So basically, what I do here is I take a layer factory. I say I want a restrictive Boltzmann machine. A restrictive Boltzmann machine is that two-bias neural network I was talking about that basically did automatic feature engineering. So it learns the features, it learns faces, it learns OCR, handwriting, whatever you can think of. It learns those things and then gives you the, and then basically what you do then is you say, OK, I want logistic regression. So what I do is I say, OK, override only the third configuration and give me softmax. So for those of you who aren't familiar, softmax is basically a probability distribution over a set of labels. So in this case, I'm saying, give me softmax. Let me basically minimize the error with respect to the guesses or the likelihood of a particular label. And then the output, the true labels are a binary matrix where you say the true result is 1. Or if I have 3 labels and it's label 1, it's 1. So 0, 1, 0, and then it says 30%, 60%, 10%. And then you minimize the difference between the two. So that is basically, that's softmax regression. That's multinomial logistic regression. What's really weird here is as of Spark 1.2, I didn't actually see multinomial logistic regression in there. I saw some talks, no code though. Kind of strange. The other thing I want to mention here is that Spark is awesome as a runtime, but I have a problem when I see classes logistic regression with LBFGS. What? Why can't I just say, give me an output layer, and the optimization algorithm is LBFGS? Why can't I just pick which one I want to use? Why do I have to change the class completely in order to give myself something that allows me to run LBFGS with logistic regression? So I emphasize a configuration-based approach here. And then what I do is I scale this out with Spark. So I minimize multi-class cross-entropy. That's the difference between, that's minimizing the true minus the guess. And then I say, OK, now let me create something. Let me create Spark DL4j multilayer. So all I do is I pass it a configuration and a Spark context. The Spark context is basically your drop-in point into Spark. So you specify your master, or you run it locally. You create your Spark context. You give that then to Spark DL4j multilayer. In this case, I'm setting up the network. You can use Spark's RDD support for shuffling, train test split, and all these other machine learning algorithms you do. Or you can use DL4j's built-in support for a lot of this already. There's a lot of overlap, and I encourage interrupt between the two. So I actually have an MLlib util class that gives you your familiar label points, allows you to predict with vectors, and all the things that you're familiar with. So underneath, for those of you who are curious, basically this is basically me using nd4j here. So basically, I actually could have a backend that delegated to Breeze or in these other linear algebra libraries. So DL4j basically just has this idea of a data set that's basically just a pair of input and output matrices. And then all I do is I say fit data set. Or in this case, I also have I also have the static invocation that's just like MLlib's. We can just say .train, Spark context, labeled points. So I have that as well. So both work. Both will give you Spark DL4j multilayer back that then underneath has a multi-layer network. So you're like, where does this come from then? So what I'd like to do now is go into the scale out part of this. So one of the things that's not apparent is I'm training. So let's think about this for a second. I'm training on core. I prototyped my neural net. I got my good F1 score. I got my good training accuracy on a certain kind of small sample size. Now I want to train on the whole data set. What does that actually look like? So hold on. So let's see, I'm just going to do this real quick. Apologies for the switching. It's like code and this and that. So one of the things I want to demonstrate here today is parameter averaging. So that's something not a lot of people have seen or even really think about because they just use whatever library they're given. So one of the ideas with Spark is this idea of workers. So basically, this is our algorithm called iterative reduce. So iterative reduce was co-created with my co-author Josh Patterson. He was employee number 34 at Cloudera and new distributed machine learning. And he came up with this in collaboration with other researchers as well. So basically, what you do, so this is a variation on Hog Wild. This is also done at Google with Google Brain. All you do is you train a mini batch. So what's a mini batch? A mini batch is just a subset of your data set. So I say, if I have 100 examples and I have 10 cores, I send 10 of those examples to each core. I then train a neural net on each core. It minimizes the error with respect to that mini batch only. And then all you do is, after that particular worker is done training, it basically sends it up to a master. So you say, output of all those, reduce. The reduce is the average part. And you do this for n iterations. So in this case, I train everything on multiple cores in Spark. And then you could also do this on GPUs or what have you. But either way, you have a neural net on each core. You have n models. You break it up. You partition it. You train. You average. And then what you get is essentially a modular neural network framework that allows you to scale out on Spark. So in this case, prototype on core. Think of one neural net that you're training on core as one worker. And scale out with Spark, where you instantiate a neural net per core, and you average. It's literally that simple. This is how Google Brain works. So in this case, this maps really well to the functional paradigm. So what does that actually look like? Iterative reduce itself in Spark is only a few lines of code. It's actually pretty easy. So what I'll do is I'll show that now. All right. So oops. All right. So let me just. I'm not used to this. All right. Cool. Okay. So. And then after this, I'm gonna kind of bring it all together, and then I'll be open for about 10 minutes of questions. Okay, so. Okay, so this is the actual. So opening up the black box here, let's just make some observations here. So first of all, I have my Spark context. So SC is basically like you see that in all the examples. SC.text file, SC.whatever. That's your Spark context. I use that to access whatever data that you're trying to train on. So then I have my configuration, and then basically what I do is I basically have the resultant multi-layer neural network that was basically averaged. So those are the main things to be concerned about. I guess one other thing of note is the broadcast here. So I don't know how many of those you are familiar with broadcast, but broadcast is basically this thing in Spark that says, let me only send data to a particular node or computer once. So what I do is I create a read-only copy of the parameters. So one of the neat things with neural networks is that basically you can treat a neural network as two parts, a configuration in a layer architecture and parameters. So the parameters are just each matrix lined up as one long vector. So what I do is I propagate a copy of the parameters after an initialization of the multi-layer neural network to each node. And then I only send it once. And then what I do is per worker, I'll instantiate it. So again, the parameters are just one long vector. So I'll break that down as well. So all I do, obviously with Java, it's not as awesome as some of these other languages. I have to do constructor overloading to give you kind of, like less verbose constructors. So that's all this is. The core here is you instantiate with a Spark context and then some sort of configuration, and then it handles the rest. All right. So here's the underlying fit. Here's one way to do it. You can just read in like a text file, and in this case, we have our points here. So the points use something called, this implementation uses something called Canova, which basically, Canova is our vectorization framework that basically allows you to take like an image or a WAV file and turn it into a CSV. Or SVM, or you can translate between SVM Lite and libSVM. So it basically gives you one interface for handling all kinds of data, and then you can basically instantiate it then with a data set, or in this case, Canova itself is actually neutral to the kind of data type. So you could actually translate it into a doubles array or what have you. But it's basically a vectorization framework. So in the usual Spark fashion, you have a function that basically does everything for you. So I do lines.map. I line over the data set. I return the points. And then I do fit data set here. So fit data set is the core. OK, so this is the meat. So let's break this down. So I basically get the number of iterations. So each neural network basically is one convex optimization problem where you're minimizing error. You terminate after n iterations. You have the count. So it's like, what is the number of examples? I have the batch size. So I say, OK, given a batch size, let me evenly partition this across the cluster. I basically calculate a batch size, make sure that basically each neural network has an evenly distributed part of the data. Because if you want the average, you need to evenly partition it. Then I use Spark's RDD repartition. That repartitions the data into even batches and gives you something that will basically make parameter averaging work well. And then here's basically the instantiation of the parameters. So I create the multi-layer neural network. You'll notice I'm just using core here. It's actually pretty simple. I'm using core. I'm instantiating the neural network. So that same configuration you were using in core when you were prototyping, you can scale out with Spark. So I create a neural network with the configuration that you specified earlier. I initialize it. That gives me my parameters. It sets up like all the architectures, debugs it, makes sure it's set to go. Then I basically grab the parameters as one long vector. So it goes through and it says RBM 1, 2, and 3 become one layer. Or this could be a convolutional neural network or whatever configuration you set up. It basically squashes it into one parameters. And then it broadcasts it to the cluster. So it says, given these parameters, let me send this to each worker. And then just some validation here, nothing crazy. And now, this is the interesting part. So I say, all right, let me just back out a little bit here. Oop. OK. So all I'm doing is I'm saying, given my partitions, run iterative reduce, in this case my parameter averaging, collapse all the vectors, and give me back basically the average. So I get back all the results, all the different parameters. I only send the vector. That's the key thing here. I don't send a bunch of other neural network architectures and all the cruft. I only send the original vector back. I send the original vector, I get that into an RDD, and then I average. I mean, it's literally that simple. I accumulate them all with that add function, and then I set up the average, or the initial vector, the first one. I sum them and then divide by the number of partitions, and then that gives you your average. It's actually literally that simple. It's not anything crazy. So, and then in this case, all I do is I say set parameters. So set the average and return that neural network, and that's iterative reduce. Dead simple, especially with Spark's functional programming paradigms. Nice and clean, not too many lines of code. Automatic scale-out tricks and everything that a distributed systems engineer needs, all in one go. So the key thing here now is prototype locally. I made DeepLearning4j such that I hand-derived the gradients myself, and I basically hand-optimized each worker to run as fast as you can think of. And then you scale that out. That's literally it. So now we have the distributed system. So we know how to scale it on Spark. So what about GPU? What about Spark with CUDA? How would that work? So in this case, this is Spark with CUDA too. This is Spark with native. Just like Alexei mentioned, all you do is you include a jar file that says I want to use native, I want to use CUDA. It's just like cross-linking with these native libraries without actually having to compile. All you do is change a line in your pom.xml, your build.spt, depending on which build system you use, and you're set to go. And then you can actually run CUDA with GPUs. Or if there's matrix library n+1 that comes out, that will also work because all I need to do is create a backend for it without having to rewrite my algorithms. So you basically have core with a set of algorithms. You scale it with iterative reduce. This will work on any runtime, Mesos, Spark, Yarn, any of these that you can think of. It's all Google Brain style parameter averaging. Thank you. Questions?
So you mentioned that there's problems that you want to do in Spark with Scala that you haven't yet tackled. But this looks fine. What's the problem?
So you, sorry, rephrase your question. So what do you mean?
You mentioned earlier that you're going off on doing this more in Scala and Spark, and that there's forks of MLlib.
So I guess what I'm saying is, so Spark itself is amazing. What I'm saying is I prefer the configuration-based approach that I'm doing, where I don't have to say logistic regression with LBFGS. All I have to say is multi-layer configuration, change one character, and I have all the optimization algorithms available to me. So I don't actually have to keep recreating softmax regression, logistic regression with LBFGS, or gradient descent, so I prefer my configuration style approach. That's all.
I have a question regarding the performance boost.
Right.
Could you compare it with other learning?
Well, so in this case, okay, sorry. So he was asking performance with respect to other tools. So benchmarks in Theano and Torch have MNIST on 4 cores. Takes about a day to train. That's just 60,000 images. I take 10 minutes with the parameter averaging approach. So I can scale out to any number of cores, or I can train on each core at once and get the results back. So what I would like to do is I want to actually release comprehensive benchmarks that actually demonstrate how fast things are, how it scales linearly, among other things. So I need to actually run full-blown benchmarks that I can actually back. So those have yet to be released, but that's actually what I'm working on next. I'd like to be clear that this version of Spark is a technology preview. There's a lot yet to be done, and I think the API could be cleaner. And I'm welcoming input into the community based on what we see here today. Sorry.
What was the biggest model that you were able to train? How many parameters?
So a neural net on average can be over 1 million parameters with just a simple MNIST. So obviously, depending on the box, you could scale out to 100 million parameters or more. Like I said, benchmarks need to be done yet. I've optimized nd4j where you can handle like floats as data types and a lot of other things. I would actually like to leverage Spark's new features as well as like their distributed storage. Because one thing actually we're going to implement is the parameter server done by Google. So they actually scaled out to billions of connections in the neural networks. So that's actually just a logical extension of iterative reduce actually. So you do parameter sharding. So there's actually things in the works to scale it to billions of parameters, but not everybody has billions of parameters. So I'm making some assumptions right now.
How do you, I missed, I don't know whether you talked about it, how did you do parameter initialization?
Oh, so in this case, that's also configurable.
Repeat the question.
So yeah, okay. So he asked how I did weight initialization. So that's another hyperparameter. So you typically do it with respect to the input and output sizes. That's one configuration. You can also specify your own distribution that it samples from as well. So that's all in the neural net configuration.
The question is, because the error surface of neural networks are periodic,
right?
You're going to need to have a warm-up step. Right? Otherwise, the individual batches may settle down to different.
Right.
Eventually, you're going to run into instabilities.
Right. Yeah. So I mean, that's where you have tricks like dropout, constraining the gradient, making sure that you don't overfit on any particular mini batch.
Those are addressing different issues, but even the Google brain work, there's a downpour that actually has a warm-up step to make sure that you're close to where you're going to be in terms of the actual global minimum.
So I'm just referring to the fact that the parameter initialization stage, you're going to need to have, or you're going to want to have at some point a serial step, just before the parallel step. Is a serial step.
Yeah, so we're going to do, so I want to implement Sandblaster as well that will have that initialization step.
All the examples that you're showing are about image analysis. So you must have shown us image analysis using neural net. Do you have you tried to analyze some other problem that might?
So so fraud detection. Well, so what kind of fraud? So he's asking about fraud detection. So or just other problems I've solved. So while I'm demonstrating image, that's the canonical example that most people can relate to. You can do anomaly detection. In this case, I've done it with long short-term memory. So or you could do binary classification, whether it's fraud or not fraud. So it really depends on the kind of fraud you're solving. Just like any neural network framework, you set up the objective function and the classification error and all that to give yourself your binary classifier, but it's relative to the data that you're throwing in. So we also support word-to-vec, glove, neural word embeddings, time series analysis. It's all in there. I just want to be clear that the main feature introspection tools right now for visualization are mainly for image and text. But you can actually just monitor the parameters and histogram them to get an idea of at least how fast it's training with other forms of data.
I missed the debugger. Say you have a debugger.
Oh, so yeah. So the debugger. Oh, sorry. So the debugger are those things that I was showing earlier with so in this case the histograms, the filters. I can show those real quick. So hold on. I'm just gonna run my one example here. I think, let's see, so I need to open that. All right, so what I'll do is I'll actually show you the interactive debugger now. So pardon me while I just run it just to make sure. Set everything up here, and then I'll run through it. Okay, so right now we're warming up, and then what it's going to do is the first thing it's going to do is it's actually going to basically pipe some output to matplotlib that will show me the histograms here. So. In this case the debugger while we're setting up here. I don't know. let me just, well, so while we're waiting, sorry? Oh, I don't know. Oh, what's going on with IntelliJ today? Let me try to run it on a simpler example. All right, 1 second. Am I not seeing it, or the dual screens has tricked me before? Oh, there it goes. So it sets it up. All right. Okay, cool. All right, so basically the first thing you do is you actually run it, and in this case, this is a restricted Boltzmann machine. So you plot the activations. So you see that I have the weights, the hidden bias, and the visible bias. So the weights are the actual connection weights. The hidden bias, in this case, the hidden bias is what you'd think of for the forward prop, and the visible bias is what's attached to the data. The key things here is you need to pay attention to magnitude. So that's that number at the top there. Make sure that that's not too large and that things are uniformly distributed, which you can also see here. So let me just, and then you close it out, and then what it's going to do next is actually bring up the images. So these are actual faces. Oops. So these are the actual faces. So what it'll do is it'll run the histograms, and then it'll actually, it's really difficult to see. If you want to see a close-up later, I'd be more than glad to show you. It's just what I was showing you earlier with those faces. So you basically debug them visually, and then this is the activations. So basically what you do with a neural network is you see how sure it is. So in this case you can see that it's relatively sure. So if it's white, that means the activations were closer to 1. If it's black, that means it's unsure and that it's uninitialized. The typical flow here is you want it to start dark, so dark and gray. Make sure that it doesn't overfit. You let it run for a few iterations, and then if it stays uniformly distributed with the histograms, and it stays gray throughout, and slowly over time gets brighter, you know that you actually have basically a good hyperparameter configuration. So that's the general flow with kind of like the debugger. That's why I suggested debugging visually, because otherwise neural networks tend to be black boxes. Does that make sense?
Inside your code.
Yes.
Oh.
So this is, yeah, so I actually have built-in tools that do all of this for you. The only thing you have to do is say, I want at every n iterations, plot. And then I basically have hooks for every individual little debugger that you'd want to build. IntelliJ. Go ahead.
I have a couple of questions. The first regarding the size of the models. I saw that you save. Thank you. I saw that you save all the parameters in a progress variable as well.
Right. Mm-hmm.
Is it limited the size of the model by the RAM
yes.
capacity?
Currently, right now, it does. So again, if you have a billion parameters, send me a pull request.
It could be a really problem because basically we imagine that we have like 1,000 workers.
Right.
And at the same time, they're sending the gradient.
Gradient back. Yeah. So in our Yarn version, we save it to disk. I said this is a technology preview because I actually wanted to get feedback from the community. I'd been talking to Sean over and over at Cloudera, and he kind of gave us an initial pass. But there's definitely still more work to do. On Yarn, I'm aware of that and save it to disk. That one's a lot more developed than the Spark version right now.
Okay, I see. The next question is regarding the configuration of the network you show. So currently, as far as I understand, if I want to change the configuration, I have to change the code. Is it
so you can actually serialize this to JSON and then just change a properties file instead.
Oh, I see.
Yeah, so very similar to Cafe.
Okay, that's it. Thanks.
Cool.
So you mentioned that part of deep learning is actually figuring out features from neural data, right? Could you elaborate a little bit how that works and if you actually use it?
Sure. Yeah, so what you saw, the output so those faces were basically the features. So the automatic feature engineering is just learning how to reconstruct the data. So if you have a feed-forward net, you're using an autoencoder or a restricted bolts machine. You have two biases, one attached to the input, one attached to the output. And basically what happens is you compute the activations with respect to the output and with respect to the input. And you minimize the reconstruction cross entropy or KL divergence of the data. And what you get is a shared weight matrix that then represents the original input. Basically is able to reconstruct the inputs. So this works for recursive nets. This works for normal feed-forward neural networks, convolutional neural networks, whatever you're trying to do.
Just to add what he asked, do you label your data first?
Sorry?
Do you label your data or how put it?
Yeah, well, OK, so like I said, deep learning is not magic. It's just like normal neural network. It's just like normal machine learning. If you're doing supervised learning, you have labeled data. So the key here is to use the RDDs in Spark to handle like labeled points or what have you for your data. One thing I want to mention though is that a lot of search-based algorithms and clustering can be done with just the output of normal neural networks. So one technique that not a lot of people know about is this idea of semantic hashing, deep autoencoders. It's not used as much anymore, but I know a lot of companies that basically use it as a form of compression for storage. This is actually what's done in image search as well as text to compress a bag of words. So you basically train a neural net with just backpropagation on reconstructing the original data. So you have a feed-forward decoder that you train. You do pre-train, 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 just like the normal neural networks. And then what you do is you create a transpose of that's a decoder, and then you minimize error with respect to all the neural network, like all the layers. And what you get in the middle is basically a neural network like a coding layer that actually knows how to compress data. So you can actually create a good approximation with reduced dimensions.
On your website, you said that you're starting running the code for LSTM. Can you be more specific?
What?
Long short-term memory.
Yeah, do I have it? It's done. It's in there.
Okay, I see.
So
because, I didn't find the link on the website.
Oh, so we're actually going to update the website for the next release. So right now we just implemented the new API that has like the layer architecture, Fiano style modules and layers, and parameters and all that as well. So expect that here soon.
I was wondering if we're going to cover nd4j separately.
So nd4j, I can give you like a quick rundown on that. The major thing with nd4j is that you have a number of backends. So nd4j itself, let me just bring up GitHub here. So nd4j itself is a very simple project. It's very similar to what you see with NumPy and MATLAB. So basically what I do is I have a series of components that give you a MATLAB-like interface to any sort of scientific computing library on the JVM. So JCUDA is supported, JBLAS is supported, and we're going to be rolling out support for Intel NKL as well as OpenCL here soon as well. So all those are backends without you having to rewrite code. So every time a new matrix library comes out, if you have one core, you write your algorithms in nd4j, and then you delegate to a backend. So that's what these modules represent here. So I support NetLib BLAS. This is the beginnings of the Scala API. I have JBLAS in here, and then a number of cuBLAS modules. So the API is the key here. So basically what I have is one test suite for all the backends. That's represented here. So this will also show you example usage as well. So basically, there's one IND array, So this is how you create an ND array. So just like everything you think of, you have lin space, you have ND arrays, you have np.create or what have you. Sorry, yeah. Here, so all you do is you have an IND array, and then all these backends implement that interface, and then you delegate to any backend you choose. And then the key here, NetLib and some of these other things have multiple backends, but don't give you ND arrays and one interface for one familiar interface for scientific computing. So if you want to work with 4D tensors, you should be able to do that. Not a lot of libraries support this though. So so here's like a basic example. So as you can see, I have like nd4j.ones, nd4j.linspace. Like basically, if it's a NumPy, I've implemented it here in nd4j. So it's a very similar initialization. And again, this is one test suite for every backend that you could think of. Obviously, I'd like help expanding this because God only knows what else you'll run into. But like the core idea is there. So you have reshape. Like it's exactly like NumPy. So one of the things I did though is I actually took some cues from JBLAS and actually made some operations on matrices more explicit. So subtracting row vectors with broadcasting, that's something that's a pretty common operation and something that should just be explicit. I have rows and columns. So you don't have to use the axis interface for everything unless you're actually dealing with ND arrays. So there's also sorting. So just like argsort with NumPy, you have that there as well. Other than that, I mean, this is it. This if at a scala interface with operator overloading could be, would look exactly like NumPy. Save some differences, but in general, it's there. I mean, beyond that, yeah, this is it. I mean, there's nothing much to it. Like, so like, see, swap axes. You have slicing. I mean, it's a matrix library. I also have indexing. So ND array index gives you intervals, gives you Boolean indexing. All that's supported as well. I mean, a lot of this needs to be documented a lot better. I'll be honest with you. I primarily created this for DeepLearning4j. I wanted an interface that was familiar to me that I used in scientific computing. So one of the things that's not very familiar to Java developers or Scala developers, maybe some of you, but functional programming, but vectorized programming. So actually, like working with vectors, making it easy to do transpose operations, and thinking in terms of symbols. So one of the things that I'm looking to implement, and if there's any mathematicians in the room, I'm actually going to be looking to support symbolic computation as well, very similar to what Theano does with automatic derivation of gradients. Other than that, I mean, I'm pretty agnostic as to what matrix library I use. I'm going to use whatever is fastest. I just don't want to have to rewrite my code every time something new comes out. That's like the idea here. Beyond that, I've also implemented some of the operations that only exist in Theano. So dimension shuffle is one of those. This one was fun. Beyond that, dimension shuffle is like a more kind of academic, but you can basically do a lot of crazy reshaping tricks. So I mean, as you can see, it's literally it looks more or less like NumPy. You have linspace, reshape. You can get rows, get columns. I support tensors, which is all in here. I mean, this is in my opinion how scientific computing should be done. I mean, it's nice and simple. Everything's a vector. I can say sigmoid. I can say tan h. Whatever linear transformation you're looking to do, it's all there. I don't know, Alexei, is there anything in particular you wanted me to show? I mean, that's really all it is. You have a number of backends, and you use one interface for matrices.
Like this backends with different functionality. Can you like?
Sure. So I can here. So one thing I can do real quick is go into. Okay. So one of the core concepts is the BLOS wrapper. So the BLOS wrapper itself is basically the primitive you use to delegate to different backends. So BLOS stands for Basic Linear Algebra Subsystems. That's actually the spec for fast matrix operations on a computer. So it's been around for a long time. It's a standard set of algorithms, and it's a standard implemented by a number of vendors, including Intel, NVIDIA, among others. So the BLAS wrapper is actually how you delegate low-level operations. Very similar to NumPy. I expose the raw primitives. So all you do to use a specific BLAS wrapper is include a particular jar file. And then nd4j will do a lookup at runtime to figure out which one it should be using. And then when you call nd4j.create, it then will create the particular backend. Let's see. Get the BLAS wrapper. Linear, scalars, wrapping different kinds of vectors, tensors. I mean, there. Cool. So the other thing is coming up is also the ability to inject your own convolution and fast Fourier transform implementations as well. So if you're into native and you want to inject your own implementation of that, you can do that as well. The idea is to have one JVM-based interface for handling all your scientific computing. And then in this case with Spark, all you would have to do to use it is run your map operations or flat map or reduce or whatever kinds of other algorithms there are there. And then all you do is you have to make there's going to be an extra step. You have to make sure to set up the particular backend on your cluster. So if you're using Spark EC2, it's not going to be quite as automatic unless you have a little bit of assistance. So there might be a little bit of manual setup. So that ideally there will ideally be some utilities that handle that, but for now, just be aware of that. So Spark by itself comes with, God, I don't even know how many machine learning libraries or matrix libraries. It has Breeze in there. There's some NetLib. I know there's JBLAS. So a lot of things I believe are supported already. I've used JBLAS without a problem on a big cluster. Pretty easy. Use Spark EC2, submit your jar file via submit jar, and you're done. All right. Cool. Go ahead.
So with the current state of the code, if I go home tonight or tomorrow on my lunch break and I want to run a simple example, where's the best place to go to follow a basic like MNIST or something like that example?
So DeepLearning4j.org has a number of examples on single core. We need to put out updated examples for Spark and Spark Hadoop and some of these other things though. The API has been rewritten since 3.2, and I need to get some better documentation out there right now. Which is why I'm saying it's a technology preview. I have a lot of early adopters on our mailing list that have been helping me along though. We're getting there. Yes. Yeah. So all the code's there. If you want basic example usage, the tests are going to be the most up-to-date thing. I mean, now that I'll say this, now that the API is stable and modular and you can plug in different components and it's composable, I'm pretty comfortable with where it's at and intend on actually like basically writing scikit-learn style documentation for this. Cool.
What's the difference with Torch?
Sorry? Oh, what's the difference with Torch? So, well, okay, Torch is written in Lua, right? I said Torch is written in Lua. So it cannot be in the same process as your Spark cluster without a lot of custom work. Whereas this integrates with built-in tools. I support different neural word embedding implementations, and everything you see is distributed. So everything will integrate natively with Spark in the same process, and you can deploy it with just a jar file. So the whole point is to work with a familiar language in a familiar environment versus Torch. I mean, Torch primarily works on GPUs and CUDA. It's a bunch of C blobs, which no one likes deploying. So it's hard. It's harder to manage. I mean, a lot of systems are JVM based. The day-to-day data scientist doesn't know Lua. The day-to-day data, I want to support a lot of these different ecosystems, but it's like I'm primarily focused on practitioners here.
So you said this one is already distributed, it's already parallel.
Yes. Yes.
So how do you do the parallelization?
So that's parameter averaging. So we use that's called parameter averaging. We use something called iterative reduce for scaling out to multiple cores. And then we are also going to implement Sandbus or LBFGS as well. So those are both scale-out algorithms that involve parameter averaging, where you have a number of workers, you replicate the model to n cores, and then you basically send the results back up to one master node that controls the aggregation of the results.
Just a quick question. Could you compare this library nd4j with other libraries like MLlib, Java, or Breeze?
So those are all backends for me, and I actually support ND arrays. So Breeze has 3 and 4D tensors, but doesn't allow you to scale out to like 6 and 10. And I give you well, that's actually a realistic workload. Like if you're working, especially if you're working with convolutional neural networks where you're analyzing video, that's 4 and 5 dimensions. So I give you a transparent interface that looks exactly like NumPy, and people who use vectorized libraries could then use. And then I delegate to a number of backends rather than, so if there's one takeaway, it's a facade. It's a facade for any number of libraries that you would want to use with ND arrays. And then I also want to add that there's supplementary algorithms in here. It's not just a BLOS implementation. You can plug in your own FFTs, you can plug in your own convolutions, or any other native-based operations. Done? OK. All right, thank you.
Thanks, guys.